Okay, so let's talk about energy diagrams. So let's start with a simple situation, which is say that you throw a ball in the air with some initial velocity, and the ball is going to stop at some h max, where the velocity of the ball is going to be 0. So let's do a plot of the potential energy of that ball. So the potential energy, as you know, depends on the mass, gravity, and the location, the vertical location of the ball. So I'm going to start with y equals 0 being at ground level. So the potential energy plot looks like this. If I'm plotting energy versus y, right, then at y equals 0, your potential energy is 0. As you go up, as your y increases, your potential energy is going up, right? So notice that in the horizontal axis, I'm plotting the vertical height, the height of the object. Okay? Now suppose that I give that ball some initial kinetic energy at the bottom, right? It has some initial velocity, and there is a kinetic energy corresponding to that initial velocity. Okay? So suppose I give it this much kinetic energy. So that means that because we know that there is energy conservation, then the energy of the ball at the beginning should be equal to the energy at any location in the vertical axis. At any y, the energy of that ball should be a constant, right? So in a plot of energy versus vertical distance, the energy should be a straight line because energy is constant, right? So if I start with this much kinetic energy, and given the fact that I have no potential energy at the beginning, that is the amount of total mechanical energy that I have. At some point between the bottom and the top, the particle would have some potential energy. Let's say that this is how much potential energy it has at some location, y less than h max, and it would have some kinetic energy. It will be moving upwards with some kinetic energy. Notice that because mechanical energy in this system is going to be conserved, this plus that should be the total mechanical energy. Okay? So that distance here plus, which is in terms of energy, plus this should be the total, which is equal to the kinetic energy that the ball had at the beginning. As the ball continues to move, the potential energy continues to grow, and the kinetic energy continues to decrease, until you hit this spot, which is h max, right, where what happens? The kinetic energy is going to be 0. The potential energy has reached a maximum value, right? And that maximum value is equal to mg times the maximum height that the ball reached. And that maximum value of the potential energy, as you can see here, should match the initial value of the kinetic energy, right? Because energy is conserved, mechanical energy, in this problem. So that initial kinetic energy, of course, is 1/2 of mvi squared. So the maximum potential energy that that ball can reach is equal to 1/2 of mvi squared. So using that, I could find how much is the maximum height reached by the ball. Just make potential energy at the end equals, energy at the end equals energy at the beginning. At the end, you only have potential, no kinetic. Initial, you only have kinetic, no potential. So you make those two quantities equal, and you find that the maximum height is v initial squared divided by 2g, which is something that we have already derived many times before using just kinematics, right? This equation, you can get to this very quickly by using the equation vf squared equals vi squared minus 2g distance or displacement, which will be here h max. Something important to point out about energy diagrams is that at the point where the potential energy meets the total energy, the mechanical energy of the object, at that point, your kinetic energy is going to be 0, right? Those points are called turning points, because if the kinetic energy is 0, the object momentarily stopped at that location, okay? The object will be going, in this case, going up, stops, and then it starts to go down, right? That's what happens to this ball. It goes up, stops at the turning point, and then turns back down, right? It was going up, stops, and then it comes back down. So that's a turning point, which you can identify, as I said, in an energy diagram by the points where the mechanical energy of the system meets the potential energy of the system. Because at those points, there is no kinetic energy left. For the case of a spring, another case of an energy diagram to consider, we chose the x-axis to be, in this problem, will be horizontal, and the origin is at the equilibrium position of the spring. The origin is at the equilibrium position of the spring, right? So the potential energy, remember that is equal to 1/2 of k x squared. If I put the axis, the origin of the x-axis at the equilibrium location. So my potential energy looks like a parabola. And if I give the object a mechanical energy represented by the blue line, some amount of mechanical energy, then, as I said before, where the mechanical energy intersects the potential energy, those are called the turning points. Because at those points, a particle, in this case a block attached to a spring, would stop. At those points, the block would stop. There is one positive A on the positive x-axis and one negative minus A. They're at the same distance because remember that the potential energy is a parabola. It's symmetric around the middle. Okay? So the horizontal line crosses at minus A and at A. And those are the points, as I said, turning points. The block on the turning point on the right, the block maybe was going this way. It slowed down because it was stretching the spring, finally stopped at a distance A from the origin, and then it starts to move back, right, pulled by the spring, passes the equilibrium point. It has momentum, so it keeps pushing, right? It slows down as it's compressing the spring until it stops, and it stops at a distance minus A on that side of the equilibrium point. Now suppose that I ask you, I give you a spring, an block, so a spring with a spring constant 100 newtons per meter and a mass of 1 kilogram, and I tell you that I want you to set that mass m in motion with 50 joules of energy. How would you do that? What would you do to that mass to give it 50 joules of energy? If I give you a ball, and I ask you, give 50 joules of energy to this ball, what would you do with that ball? You throw it, right? That's a possibility. Another possibility would be you grab the ball from the ground and you lift it until it has 50 joules of potential energy. When can you tell that it has 50 joules of potential energy? You use the equation mgh, right? Depending on the mass of the ball, and g is 9.8, you make sure that the height is such that mgh equals 50 joules, right? And then you would say that ball has 50 joules of potential energy. Or I throw the ball with a velocity that such that 1/2 of the mass times the velocity of the ball squared equals 50 joules, right? So that's for a ball. Now think about it for a spring, a mass attached to a spring. What do I do to that mass to give it 50 joules of energy? What are the possibilities? You can stretch the spring or compress it, right? By how much? So let's use K, 100 newtons per meter, and let's use for the mass of the object 1 kilogram. How much do I stretch or compress that spring? So I want to make 1/2. If I just stretch it, I give it 0 kinetic energy, but I'm going to give it some potential energy. So I'm going to make 1/2 of K, that distance that I stretched it, I'm going to call it A squared. So 1/2 of K A squared will be the potential energy that I give it. And I want to make sure that that's equal to the mechanical energy, which is going to be 50 joules. I want to give it 50 joules. So in terms of the energy, of the mechanical energy, I can solve for the distance that I need to stretch it or compress it, right? Solve for A in this equation, and you get A equal 2 times the mechanical energy divided by K, and you take the square root of that. So that will be 2 times 50 joules divided by 100 newtons per meter. So that gives you 100 joules divided by 100 newtons per meter. That's going to give you a meter squared. Square root of 1 meter squared, it's 1. All right, so to give it 50 joules of energy, you will have to stretch or compress that spring by a distance of 1 meter. Okay? When you do that, you're giving the system that much energy, you let it go, and from that point on, that mass with the spring are going to move in such a way that they always, at all times, will have 50 joules of energy. Okay? Sometimes all of the energy will be kinetic, Sometimes all of the energy will be potential, but every time when you add the kinetic plus the potential, you will get 50 joules. What's the maximum velocity that that object is going to have if I set it up with 50 joules of energy? And where does that maximum velocity occur? So I stretch it. Let's say that I put it here 1 meter away, right? I let go it. Okay, where does it reach maximum velocity? At the equilibrium, when it's passing the equilibrium point, because at that point, the kinetic energy is a maximum. Right? If this is the mechanical energy and this is the potential energy, right? At this point is when you have maximum kinetic energy. Here you have 0. You're growing, the kinetic energy is growing, reaches a maximum. So that's at the equilibrium point. When there is no potential energy. That makes sense, right? Because potential plus kinetic must be 50. So at the point where the potential energy is 0, you have kinetic equals 50. That's the maximum that you can have. So you would say that at that point, the energy of the object is only kinetic. So 1/2 of the mass times the velocity maximum squared should be equal to your total amount of energy, which you started with. This should be 50 joules, right? But I want to write it just in general in terms of A, because this is an equation that is going to show up again when we deal with oscillatory motion. So we're going to get that the maximum velocity spring is going to be given at the equilibrium point. It's 1/2 of Ka squared. So there is a connection between the amplitude of that oscillation of the spring and the maximum velocity given by the square root of K over M. So the more you stretch this spring, right, and let go of it, the faster the object is going to go at the equilibrium point when it crosses the equilibrium point. Now, in general, the potential energy of an object could have any shape. It will depend on what interaction are you talking about. This could be the potential energy maybe in a molecule, maybe different parts of the molecule feel in the presence of the other part of the molecule, different atoms experiencing an electric interaction or van der Waals force or something like that. And those interactions can have some potential, right? So the point is that when you have the potential energy, when you know this information, you know a lot about how that particle can move. The next piece of the information that you need is how much is the mechanical energy that particle is going to have in that potential. Okay? In more concrete terms, maybe more familiar terms, this could represent the gravitational potential. So how do I make sure that I have a gravitational potential that depends on position like this? I can just do a little landscape, right? This could be a wire that I bend in exactly that shape. And I put a little bead that can slide on that wire. Or this could be just the ground, right? And this is a little hill, a valley here, another hill, a valley, and so on. That would represent the potential, gravitational potential energy of the object. So you put a ball there, and the ball is going to move in this potential, right? Now, how does the object move depends, as I said, on not just on the potential energy profile, but also on the total amount of mechanical energy that the particle is given. Okay? So suppose that I give that particle some amount of energy described by this yellow line, mechanical energy 1. So how does that particle move? First thing to notice will be that there is one turning point for that energy. In that potential, for that particular energy, the particle has one turning point. Right? It occurs when the potential energy crosses the mechanical energy line. At that point, the kinetic energy is equal to 0. So in this potential, how do I give a particle that much energy? I would maybe start with a particle over here, and I will hit it, right? Give it some initial kinetic energy, so that's my total energy. So when the particle comes in, the kinetic energy increases, decreases, increases again. The particle climbs up this steep hill, and then it stops here. And then the particle is going to roll down, make that, right, and leave the way it came. Okay, so that particle comes in, hits this wall here, and it comes back. So that's only one turning point. And this particle is not bound, right? Because it's not required that this particle stay in any particular location. It can go from plus infinity, can come back to this point, and then it can go out again to plus infinity. So this particle is not bound. But if that particle that I'm shooting into this potential had been given a different value of the mechanical energy, say E2, then the motion will be different. Okay? Because if this is the total energy that I give to this particle, then you see that there is 1, 2, 3, 4 turning points. At those points, the particle has to stop and move back. Right? So in the analogy with the profile, like a roller coaster kind of thing, you start with a ball or with a card in the roller coaster here. To give it this much energy, total energy, what the easiest thing to do would be to just put it here. Right? Give it that much potential energy, zero kinetic. So I let go of it, I let start from rest, and this is how much kinetic, potential energy it's going to have, which is the same as the total energy. So it starts rolling down, picking up kinetic energy. Why does it pick up kinetic energy? Because this plus the kinetic is the total, right? So you start with zero kinetic, it starts to grow, 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 and at this point, you have the maximum kinetic energy. Then the particle starts to climb up the hill, slow down, and then it finds this turning point, at which point it's going to stop, the kinetic energy is zero, and then it starts to roll back down. It passes this point, rolls back uphill, stops here, that's where you let go of it, and then it rolls back down. So the particle is going to stay moving between this point and that point. It will continue to oscillate forever if there's no friction. We'll do this. Okay? But I could give in that potential, I could give the particle the same energy by locating it right here, starting with the particle located there, and I let go of it. So now the particle rolls down, it goes to a deeper valley, right? It goes lower, picks up more kinetic energy, but again, it's going to lose it until it stops at this point, and then it rolls back and forth. So the particle is forced to remain oscillating on this well, or remain oscillating on this well.
So the particle can be on the middle one?
So the particle can never be found here, because if the particle were to be located at this point, it would have this much potential energy, which is greater than the potential energy with which you started.
Okay.
So that would give you like negative kinetic energy, which is impossible. So this is prohibited for the particle, this region. At that energy, this part of the potential would not be explored. This part of the potential will not be explored. This part would not be explored. Okay? So that's a classical particle. If this was a quantum mechanics class, I would tell you that yes, the particle is going to be confined here, but sometimes the particle can tunnel through this potential barrier, and you will find the particle sometimes here. And it would stay there for a while, and maybe you make a new measurement sometime later, and you find it here. The particle will be oscillating back and forth, not oscillating within the potential, but also between the potential wells. You say that the particle tunneled through the barrier. Okay, so those are the two regions for this classical particle, we would say, that obeys Newtonian mechanics, where the particle has to be confined. So we're saying that for this energy, the particle is bound. It's bound to be either here or here. The motion for that energy is bound. At this energy, if I had started that particle with an even lower energy than E2, maybe at this level, then two turning points, the particle is again bound. Right? It can only be found within these 2 points. All right? So an energy diagram tells you a lot of information about how a particle is allowed to move. Right? It tells you where you will find it, tells you where there is equilibrium for that motion. But you need to know the energy. That's the main message here, that the energy makes a difference on how the particle is going to move. So in a potential energy diagram, we mentioned this before, there is points that are equilibrium. So at this point, we have an equilibrium point, right? Because if the particle is displaced by a small amount away from the equilibrium, what it tries to do is go back to it, right? It doesn't go far. That's the basic idea. So this is an equilibrium point that is stable, because the particle just stays there around that point. Okay? If it loses, if there is some sort of friction in this system, the particle will lose energy until it settles at the bottom of the well. So it's always going to be found there. That's called a stable equilibrium point. there's another equilibrium point, stable, at this bottom of this well, right? The same thing will happen here. Particle will not deviate too much from the equilibrium point if there is any perturbation. But there is another equilibrium point. Again, use the analogy of the landscape. I can put a ball on the top of this hill, and it's not very stable, but I could put it there and keep the ball for a little while. But eventually the ball is going to roll one way or the other, because there's perturbations always happening. A little bit of wind, you know, a little bit of ground shaking, and the ball goes one way or the other. So that's a equilibrium point, but it's an unstable equilibrium point.